Hello everyone. In this lecture we shall discuss the errors out of a numerical approximations. As you know, the numerical methods give the approximate roots or approximate solutions which is not the exact solution, right? Which is not the exact solution. As you see, suppose you are 1 by 3. Okay, coming to your 1 by 3. So the exact solution is 0.3333 continued up to infinity. So this is the exact x, the exact solution, what I call the true value, right? Now if I round it up to 4 decimal places, it will be my 0.3333 up to 4 decimal places. So this is my approximate x, the approximate I write xa. Okay, now this difference of these two. Okay, now if I take the difference of these two, right, difference of these two, then this is my error. So this my error will be xt minus true value minus exact value. Okay, if you subtract it, it will be 0.0000333 and continued. Okay, so this is the error. So what is the error? So the difference of this true value minus the approximate value. Now sometimes while we round it off, you see here, we round it off here, 3.1416. It is 3.1415. Now it's superior here. Now if you subtract it, there will be a negative sign, right? So we should write the error in absolute form, right? So as you understand, error is true value minus the approximate value. Now we should find what is the absolute error, right? Absolute error. To deal with the negative sign, absolute error. Okay, the absolute error will be here E mode. It is denoted by modulus of E. That means true value minus exact value, we take the minus approximate value, right? Approx. Now we take the modulus of this. So this is my absolute error. Now coming to a relative error. Coming to a relative error. Relative error. We denote it ER. We denote it ER. So this will be absolute error by true value magnitude. Okay. So this is xt minus xa modulus divided by here xt modulus, right? Then coming to here percentage of error, right? Percentage of error. Percentage of error. So I write it EP, E subscript P. So this is ER into 100. ER into 100. Okay. So ER is, you substitute ER from here. So now the thing is that, you know, the exact numbers, while we classify the numbers, we have the exact numbers 2, 4, 9, 7 by 2, 6.35, etc. If we are getting solving and we are getting exactly 2, we don't have any error. But while we approximate it, okay, as I have told you, 1 by 3 is 0.3333, it is continued up to infinite. Root 2, 1.41, 4213, so on, continued, and we rounded it here, right? And 3.5 is 3.14159 to 22 by 7, so we rounded up to 4 digit. Okay, later on I will tell how this rounding will be made, right? What is the principle of rounding? Clear? So now from you see here absolute error. While we evaluate the exact solution or with the approximate solution out of a physical situations, we have some measurement units. So this absolute error or your error, right, or your error, so these are having the unit of the measurement, right? But these two, your relative error and percentage of error, right, so these are having no units, right? These are having no units, means while we compute this, we commit 20% error, so we don't need that unit of the measurement there, right? So now before the details of the discussion of these errors, right, let me to introduce myself, Professor Kumar Paikray, currently working as a professor in the Department of Mathematics, Veer Surendra Sai, University of Technology, Burla, Odisha, India. Okay. So now without much delay, let us have our details of discussion. So, as you see here, we now approximate up to 4 decimal places. Okay. So up to a certain degree of accuracy, we need to write it. So now in approximation of errors, up to a certain degree of accuracy, right, it is important to know what is the significant digits, right, significant digits. In fact, if I say suppose my x approximate value is my 0.00345. So it is given up to 5 decimal places. Okay, places. However, the degree of accuracy, it is correct up to 3 significant digits, right? So it is correct up to, however, it is correct up to 3 significant digits. 3 significant digits, right? 3 significant digit. So always we should write the number, okay, in standard form. So we should rewrite it. Here x approximate value here will be 0.345, okay, into 10 to the power minus 2, right, 10 to the power minus 2. So we should write it, right. So in general, while we write this way of writing a number is called the floating point number, right? It's called the floating point number. Okay, here what is the base? The base is 2. A base is 10 here, so it is decimal. If this 10 is replaced by 2 here, then it is binary, right? If here 10 is replaced by 8 here, then it is octal number. If it is replaced by here 16 here, then it is hexadecimal number. Okay. So in the memory of the computer, right, basically the number is fitted in terms of the binary having 2 bits. So in binary number we have the 2 bits 0 and 1. In octal number we have 8 bits 0, 1, 2 up to 7. Possible reminders after division by 8, right? And here it is 0, 1 up to here 9. Then A for 10, B for 11, C for 12, D for 13, E for 14, and F for 15, right? So these are the digits in hexadecimals, okay? And for binary we have these bits. So in the memory of the computer, right, the binary may be fitted or in any form of the numbers, but generally we are habituated in writing the number in the decimal form, right? So what is a floating point number? I would like to say this floating point number, the general form is 0.d1, d2, d3, so on dn into I say some beta to the power e. So e is here exponent here, as minus 2 is here, e is my exponent here, okay, exponent here, and here beta is my base here, okay. If base is 10, it is in decimal form, right? So why it is called a floating point number? Because we can adjust it, right, by taking this beta to the power e, by changing it, we can plot this point here. We can plot this point in any place. As the point was here, right, we write this point by adjusting it. So that is called a floating point number. In general, we write it or the reversion of this, we may say it minus, it is d of minus 1, d of, the reversion of this is d of n minus 1, okay, d of n minus 1, d of n minus 2, d of n minus 3, so on up to d0 point, d minus 1, d minus 2, d minus 3, up to d minus n. It should be d1, it should be d1, d2, d3, okay, up to dn, right? Why I am writing like this? Because suppose I say a decimal number. For example, I say one decimal number, suppose 246.79. How will express it? You will express it 200, right, plus 40 plus 6 plus 0.7 plus 0.09. In that way you will write it. It should be minus 1, minus 2, minus 3. Okay, in any way we write, but for a better convention, okay, to correlate it, you see here, as I have told you, n is 3 here, n is 3 here, n is equal to 3, say, for this point of view, it is 2 into 10 to the power 2, because n minus 1, okay, plus here 4 into 10 to the power 1, plus 6 into 10 to the power 0. Okay, so now for this part we have here 7 into, it is minus 1 I have told, so 10 to the power minus 1, and plus next will be 9 into 10 to the power minus 2. So this is what it is written like this. But the better form is this, okay, better form is this, because we able to plot the point on the basis of the adjustment of beta to the power e or 10 to the power some e. Okay, so now coming to more about the significant figures. So let you write, consider a floating point decimal number of this form 0.d1, d2, d3, so on dn into 10 to the power some e, right? Now the moment this d1 is not equal to 0, the moment d1 is, if d1 is not equal to 0, then the digit in a normalized form, then the number is in normalized form, okay, normalized form. So once the number is in normalized form, then all the digits are significant, okay, then all the digits are significant, right? So as I have told you here, you see here, so you see it here, so this is not equal to 0, okay, so then all these digits here are towards the right are the significant digits. If I write, for example, if I write suppose 2.5436, so here if all the digits are significant, or I can write it 0.25436 into 10 to the power 1. You see all the digits are significant here. So how many significant figures? 1, 2, 3, 4, 5 significant figures, okay. Suppose if I write 0.02, 0.004 or 2057 here, okay. So you see, so which are the significant figures here? This and this 0 is significant, but these 2 0 are not significant, because we will rewrite it here 0.42057, right, into 10 to the power minus 2 here. So you see, so this is my d1 is not equal to 0 here now, okay. So now all the digits are significant here, so this 0 is significant here, okay. So how many significant digits here, significant figures? So there are 1, 2, 3, 4, 5 significant figures, okay, significant figures. So these significant figures play an important role while we approximate the numerical results. Now let us discuss one important problem. Find the smaller root of this using 4-digit arithmetic, okay. So you know here ax square plus bx plus c is equal to 0. What is the root? It is a quadratic equation. The root is x is equal to minus b plus and minus root over of b square minus 4ac by 2a, is not it? So now the moment the negative sign is here, okay, then it will be x is equal to b, okay, minus plus, or that plus and minus root over of b square minus 4ac divided by 2a, right? So now this is being minus of b, I write it. So what is the smallest root here? So out of this, the smallest one will be, x will be b minus root over of b square minus 4ac by 2a. So this is my, as it is asked, what is the smaller root here, okay? So this is my smallest root, smaller root, right? So now if I rewrite this, if I want to rationalize it, okay, so it is b minus root over of b square minus 4ac root over into b square plus 4ac root over divided by your 2a into root over of b square. It is b plus root over of b square minus, just one second. So just in order to apply the a square minus b square formula, a minus b into a plus b. So now it is simplified. It will give you b square minus 4ac divided by 2a into b plus root over of b square minus 4ac. So now this b square and b square cancelled. Now this will be my here 4ac, okay, and it is cancelled. It is 2c by b plus root over of b square minus 4ac, okay. So this is my the smaller root also, the smaller root. Let it be my equation double star and let it be my equation star. So I may use this formula, okay, or I may use the reversion of this formula. We see out of these two formula, okay, what difficulty we are getting in which formula. Let us see now. So now what is my a here? My a is 1, okay, and my minus b is 400 and c is here 1. So I write it in floating in 4 digit arithmetic. 4 digit basically means we write the significant digits. We have here a is equal to 1, b is equal to 400 and c is equal to here 1. So I write it in 4 digit arithmetic means 0.1000 into 10 to the power 1, and it will be 0.4000 into 10 to the power 3, is not it? It is 0.1000 into 10 to the power 1. So now in view of the formula number star, our b square minus 4ac root over, let us find, and we find b square minus 4ac. This is the formula, okay. So we need also b square minus 4ac. So I need to find b square minus 4ac now. So what is my b square minus 4ac? It is b square means 0.1600 into 10 to the power 6 minus 4ac means 0.4000 into 10 to the power 1, okay. So this is, if I subtract it, so if you subtract it, it will be 0.1600 into 10 to the power 6, because you see this is a very large number while we take this square, and this 4ac is very small. So up to 4 digit arithmetic, if you subtract it, it will be this much, up to 4 digit accuracy, okay, up to 4 digit accuracy. So now if I take this root over of this b square minus 4ac root over, then this will be my 0.4000 into 10 to the power 3. Now in view of star, from here star, okay, here x is equal to here this smaller root is b minus root over of b square minus 4ac by 2a. In view of star, here x will be is equal to b minus b square minus 4ac root over by 2a. I substitute these things, so I will get it simply 0.0000. I am getting this, okay. However, this is not a root. Error is quite high error, okay. Here high error you will find it here. So now in view of from double star, okay, here x is equal to 2c by b plus root over of b square minus 4ac. If I substitute all this thing here, it is 2 into 0.1000 into 10 to the power 1 divided by here b will be 0.4000 into 10 to the power 3 plus 0.4000 into 10 to the power 3. So if you simplify it, it will be 0.2000 into 10 to the power 1 divided by 0.8000 into 10 to the power 3, and if I simplify it, it will be 1 by 4, 0.25, so it is 0.0025. okay, so this is the correct root, because it will satisfy this equation, the error will be less here. Okay, so this is the answer. Okay, clear? So this formula, we rationalize this formula, it is a better formula than this, right? So now let us discuss the error. Now coming to the error, I just repeat it. As you know, your error is equal to your true value minus approx value. Okay, or we write it by, I denote it here true value, I denote it my approximate value. Okay, then your absolute error is here simply the magnitude of the error. Okay, so that is your xt minus xa mod. And what is your relative error? This is equal to error mod error magnitude by true value magnitude. So this is equal to xt minus xa mod by your xt mod. Then coming to the percentage of error. So this will be relative error into 100. So as I have told you, these two are free from unit of measurement. Okay, from unit of measurements, right? So let me to solve one example. So coming to an example, so I denote the error by E, absolute by E mod, relative by ER, and percentage by EP. So let X is the approximated by this. So this is my true value is 0.025, and it is approximate means it is my approximate value. You find E mod and relative error and percentage of error. Okay, so what is your E coming to the solution? Here E will be, so now here xt is equal to 0.025 and x approximate is equal to 0.02. So what is your error? Your error is xt minus xa is 0.025 minus 0.02. So this will be 0.005. Okay, so now what is my E mod? E mod is not going to be same, going to be changed. Here it is 0.005. No negative sign, only negative will be converted to positive. Then it is my ER. It is my E mod by xt mod. So my E mod is 0.005 and my xt mod is 0.025. Okay, if I divide it, it is my 0.2. And what is my EP percentage of error? It is ER into 100 is equal to 0.2 into 100. That means here 20%. Okay, so we commit. So on this basis we write, we commit 20% error in approximating 0.025 to 0.02. Okay, so in approximating this, how much error we are committing? This means it is free from your unit of the measurement. Okay, in any form. Okay, so as I have told you, this relative error and percentage error, these are free from the units, while the error or absolute error are expressed in terms of the units. So now if I solve one example, for example, if x is equal to 3.1416 is correct to up to 4 decimal places, okay, 4 decimal places, then what is the error? Then the error will be, okay, half into 10 to the power minus 4 will be 0.00005. okay, this much of error will commit. Okay, so now what are the different sources of error? So now we classify the error. Okay, so generally errors are classified into 3 types. Okay, basically errors are classified into 3 types. three types. One is here computational error, right? Second one is the truncation error, and third one is here inherent error. So coming to the computational error, as I have told you, the digits 1 by 3. Okay, 1 by 3. It is 0.3333 of infinitely many. If a memory of a calculator or a computer is suppose up to 10 digit accuracy, then we are omitting the remaining 3333 we are omitting. So we will commit error. So in that way, this computational error will come out. Okay, truncation error. If we will have our Taylor series expansion, it is infinitely many, but we are writing up to certain degree of accuracy. Then inherent error, it is already present itself in the problem. Okay, it may be due to some issue with the physical situations or some issue with the limitations of the computational devices. Okay, so let me to discuss the details of the individual cases. However, we should be emphasis on this computational error. Now coming to the type of error. Okay, as I have told you, the classification of error, we have computational error, truncation error, and inherent errors. Now the computational error is most important for our discussion point of view. So this type of error arises why? Now, during the arithmetic computation due to finite representation numbers. Okay, so 1 by 3 is non-terminating up to here infinity here, but we rounded up to certain decimal places. So we are committing the error. So such errors can be classified into the followings. One is the chopping error, rounding error, and third here significant error. As I have told you, right, while we bring the number to normalized form, right, then the significant digits becomes less. So in that way I have already told. So now coming to the chopping. So in chopping, what will happen? The undesired part is removed. The undesired part is removed. Okay, without any change to the number. Suppose basically the numbers we are writing it 0.d1, d2, d3 up to dn plus 1 and so on. Suppose we want to keep it up to dn. Okay, then remaining part we simply throw it out. Without any change. For example, suppose I have a number is 5.46239576. So suppose I want to round it up to, I want to keep it up to 4 decimal places. Okay, so I will simply write it 5.4623. That means this undesired part is simply removed. Okay, it is thrown out. Okay, without any change to the system. So this is what the chopping here. Now coming to the rounding. Now the undesired part is removed, subject to a little change in this existing part. So in rounding, right, the undesired part after nth digits are removed. Okay, under the following rule: if the undesired part is less than half a unit means 5 or 50 or 500 like that. Okay, then your dn is replaced by dn. No change here. For example, suppose I say 5.429 here 376. Right, I want to round it up to 4 decimal places. I want to round it up to 3 decimal places. Up to 3 decimal places I want to round it up. Then what will happen here? You see. So I want to keep it up to this. So now this is my undesired part. This undesired part is less than my 500 here. Half a unit as I have told. Okay. So that means this a 1 will be added to it. Okay. Or let it be my 8. let it be my 8. So then it will be my, what will be my approximation? So this approximation of the number is 5.429, means 428. Okay, means unchanged. It is no change. Okay, whatever there is there. For example, suppose I say 27.36724. Then what will happen here? I want 3-digit accuracy. So what is the undesired part? Undesired part is 24. So half a unit is 50 here. So less than 50. So without any change, I write it the same thing as 27.367. No change here. Suppose it is 2.693. Suppose I want to round it up to 2-digit accuracy. So this half a unit here is this less than here 5 here. So it is simply 2.69. Okay. So here if the undesired part is less than half a unit, then it is same as your chopping. It is simply removed without any change. If it is greater than half a unit, then what will happen? Here dn, the nth place will be replaced by just 1 is added to that place. Okay. Suppose for example if I have suppose 5.42837 I want to keep it up to 3-digit. I want to keep it up to 3-digit accuracy. Then what will happen? So this undesired part is greater than half a unit. Okay, is greater than half a unit, right? So thus 1 is increased over here. It is my 5.429, right? So dn is replaced by dn plus 1. Suppose it is 26.27985. I want to suppose write it up to suppose 3-digit accuracy. Then what will happen? So this undesired part is greater than half a unit. So this 9 will be increased by 1. Okay, so this 9 will be increased by 1. So it becomes here 26 point. Okay, 480. Okay, because if I add 1 here, 9 plus 1 10 is 0, carry 1, it is 8, 4, then it is 26 point this. Okay, so this is what here rounding in this case. Now if exactly half a unit, then what will happen? If it is exactly half a unit, exactly equal to 5, that means I mean to say here dn plus 1 is exactly 5 here. Then what to do? Okay, if dn is equal to even, no change. If dn is equal to odd, if dn is equal to odd, then just dn is replaced by dn plus 1, just it is increased by 1. For example, suppose you have 23.4257, right, 8. So now suppose I want to keep it up to 2-digit accuracy. I want to keep it up to 2-digit accuracy, right? I want to remove this part, suppose. So I removed. So now this is my dn plus 1 is exactly 5, but this is being even. Here. So no change means it is here 23.42. Suppose I have 23.43578. Okay, now this is suppose my, I do not want to keep it. So now this is being odd here, and dn plus 1 is my exactly 5 here. So I should write it here 23.44. Just 1 is increased over here because odd. If odd, then increase. Okay. Now suppose one more example. Suppose I am having 2.589951. Okay, and I want to keep it up to this. I want to omit it. Okay, so now it is my exactly 5. dn plus 1 is my 5. So it is a odd one. So I want to increase by plus 1. So I want to add just 1 here, right? If I add it 1, it is 2. It is my 9 plus 1, it is 0. Carry 1, it is again here 0. So now it becomes my 9. It will be my it will be my 2.5900, right? It will be my 2.5900. Okay, suppose I have one more example. Suppose 52.325 here, right? So now I want to keep it up to this. I want to omit it. Okay, so now since this is my even now, so this will my 52.32, no change. If suppose my 52.375, I want to omit it. Okay, so now this is being odd here, so this will be 52.38. so this is because of your rounding. Okay, so rounding under these three cases. Now next coming to, now I repeat the significant errors. As I have told you, the accuracy of an approximation is determined by the number of significant figures, but simply not by the number of decimal places up to which it is given. For example, if x is approximated to 0.00345 is given up to 5 decimal places, but it is accurate, up to 3 significant figures. Okay, it is accurate up to 3 significant figures, and we write it here, 0.345 into 10 to the power minus 2. So that this is accurate up to this, right? Not up to this 5. So now coming to the truncation error, right? It arises due to replacement of an infinite process by a finite one. For example, if I say the Taylor series expansion, okay, approximation of a function by Taylor series expansion, right, up to a certain degree. You know, this is infinite series. So for example, if I ask you e to the power x, so what is the Taylor series expansion here? It is 1 plus x square by factorial 2 plus x cube by factorial 3 plus x4 by factorial 4, so on. It continue up to infinity, but if I want to write it up to third degree, right? If I want to write it up to third degree, approximation up to third degree, then will be my e to the power x up to third degree will be 1 plus x square by factorial 2 plus x cube by factorial 3. Okay, so now this is my this e to the power x itself is my x true value, but my this now it is approximated like this part is my x approximate value. Okay, so now this truncation error here is the truncation error I denote it by t, will be my this minus this xt minus xa, and this truncation error bound, okay, truncation error bound means this mode, t mode, I can make it okay, some constant. So I need to search what is this k, to find this k, So if it is asked find the error bound, then we need to find a k, upper bound of that. But for truncation error, this difference is enough. Now coming to the last type of error is my inherent error. Now coming to the inherent error, okay. So these errors which are already present in the statement of the problem, okay, before we solve it. Why this occurred? Now this may be occurred because during the approximate, suppose 1 by 3, we are writing 0.3333, but it is never ending. Pi, we are writing 3.141, but it is never ending, right? So because we are taking the approximate data, or due to the limitations in mathematical tables or calculators, a calculator is having, suppose the memory is fixed up to 10 digits, then we are committing the errors again. Digital computers, accordingly the memory are being fixed to certain digit, and accordingly a physical situations, while we set a physical problem, derive a physical problem out of a physical situations, there may be some error incurred in the parameters or in the assumptions, okay. So however, this can be minimized. However, these errors can be minimized. How will minimize it? If you use a better computer, right? By taking better data, or by using high precision computers. Okay, high precision computers, this can be minimized. Okay, now let us see what are the sources of error and what is propagation of error. So now coming to the sources of errors, as I have told you, in a numerical process, the sources of errors may basically due to the followings. Okay, inexact mathematical formulation of the physical problem, as I have told you. Now error in data which are obtained from the experiment. Okay, error associated with the numerical methods. As I have told, the rate of convergence of the numerical methods. So if you solve a problem by NR method, it is quick, then by bisection. Okay, so the error already exists in the method itself. Rounding of errors, as I have told you, non-terminating numbers are rounded up to some finite places. This is because of the finite precision computing process. Okay, so these are the limitations, and from these sources the error will occur. Now the propagation of errors. The error at one stage of computation may adversely affect the subsequent calculation. Okay, if we get the error in one step, in the subsequent stage it may have serious complication issue, right, known as the propagation of error, and may causes serious problems in numerical process. And such propagation may be due to error magnifications. Error magnification, what do you mean by that? The magnification of error, that means multiplication, right, by a large number, or division by a small number, right. It will magnify the error. Loss of significance, as I have told you, to bring the number normalized form, right, we write the significant digits. So now how this will occur? Now subtraction of two equal numbers due to rounding. This is basically due to subtraction of almost two equal numbers. Why this happened? Due to rounding. Since we are rounding up to certain decimal places, due to rounding, right. And negligible addition. Negligible addition means we are adding a very small number, right. Addition of a much smaller number, right, or subtracting a number from a very large number, okay, large number, as we did in this example, b square minus 4ac, right. So these are the propagation of error may be due to the following aspects. Okay, now the summary of this discussion is, in a numerical process, the error occurs during why this occur? Because we are approximating the solution, right, and it is differ from the original solution with some little bit of error. So this error is true value minus the approximate value. So basically the errors are of three types. Computational error, it is due to the computational problem limitation of the your scientific devices, right. And inherent error, it is already present in the problem itself. And your truncation error, infinite series we are writing up to certain degree, or we are approximating an integration by the finite summation process. Okay, so in this way this is the error. With this, my appeal to all of you is that if this lecture is helpful to you and interesting for you, please like and subscribe to this channel. This will boost my motivation to prepare subsequent lectures for your benefits. With this, I close this lecture. So thank you all. Have a nice day.